Shall we connect? ಅದು ಇದು ಕೊಟ್ಬಿಡ್ತಿದ್ದೆ ದಿಲೀಪ್ ಕೊಡು.
Good morning, everyone. On behalf of Rao Hall of Science, Education Technology Unit, and Fellowship and Extension Program, Jncasr, I welcome you all to today's program. And I request Professor Vidhyadhiraja, Dean, Professor and Dean, Fellowship and Extension Programs, Jncasr. So, over to you, sir.
Good morning, everyone. Welcome to the celebration of National Science Day at Jawaharlal Nehru Center for Advanced Scientific Research. And most of you will already know that we celebrate National Science Day to mark the discovery of the Raman effect by Sir C.V. Raman, which was done on February 28, 1928. So, this year's theme for the National Science Day is the future of science and technology initiatives, impact on education, skills and work. And today we have an exciting program lined up. We have two speakers from Jncasr, Dr. Bivas Saha and Dr. Peter Sebastian. And both of them are sort of doing a lot of translation from basic science and technology and combining these two together. So today you will hear talks by them. And let me start by introducing the first speaker, Dr. Bivas Saha. So Dr. Bivas Saha completed his bachelor's in science from Jadavpur in 2007 and then came to Jncasr, did his master's in sciences and finished that in 2010. From here he went to Purdue University to pursue a PhD, and from then he did a postdoctoral fellowship at University of California, Berkeley. And since 2018, he is an assistant professor in International Center for Material Sciences and the Chemistry and Physics of Materials Unit at Jncasr. His group is named Heterogeneous Integration Research Group, and his research interests are nanoscale energy transport, conversion, energy efficient electronic sciences. And he also, today he is going to talk about nanotechnology and new materials from energy security to artificial intelligence. Dr. Bivas Saha.
Okay, thank you. Can you hear me? Yeah. Thank you so much, sir, for the introduction, and thank you all who are online or who are present here. So best wishes for this National Science Day. So the title of my talk is Nanotechnology and Artificial New Materials from Energy Security to Artificial Intelligence. So when we, in this auspicious day, when we look at or when we celebrate science, let us look at the broad picture of our societal development. And what here we see is human population growth over the last 2000 years. So what I have done here specifically is, because of time, showing you from somewhere between last 1000 years. So here you see different regions of the world, and you can clearly see that most of the population in those 1000 years back were primarily located in India and China, and that has been the case for most of the human history. So let us look at what happens as time passes on and how much population is added and which parts in the world. So as you can see, most of them are added in China and India. Europe, some, but in America, practically none. So as time will go on, you'll see different historical events that are taking place. The Silk Road, that the great Chinese civilization, some decline in the world population, North India becoming repopulated. And that's about the time around 1500, 1600, where some civilization, some growth in population is taking place in Americas. So as you can see. So, and then look at what happens after 1800 or 1850. There was suddenly an enormous population explosion, not only in the India and China, but also in the Europe, America, in the South Americas, in Africa, and this is what we are looking at for a projected 50 years from now on. So there is an enormous growth of population that has taken place over the 100 and 200 years. And if you look at what world population today, This is the population density. India, China dominating. Some parts of Europe also having a higher population density. And look at this Americas, the West Coast, the East Coast, and the Midwest, and some other regions. What is important to notice is that if I now plot on the same graph the energy consumption of different regions in the world, and energy consumption can take it as an approximate for societal progress, how much the GDP growth is, the lifestyle is, and various aspects of life, you will see a stark contrast. Now look at this, the curve which is taken by NASA at night. This really corresponds to how much energy is spent and which region in the world per capita basis. So again, American East Coast and West Coast dominating. So they are the one that consuming the most energy per capita. Then Europe, India and China, of course there are, but look at this, in South America, in Africa, there is practically none. And compare the energy density that a person, average person spend in Americas or in Europe, the energy density caused by India and China is also much small. Now when we talk about sustainable development also means that different regions of the world will try to spend, their lifestyle will become as good as say in America or in Europe. But think about fact that what if these people who are in the South America, which are 150 million, how about in Africa, which are 1.2 billion, and then in India and China, 1.3 billion and 1.3 billion each approximately start living a lifestyle which is as good or as equivalent as America or in Europe. Well, then we have a really major problem, and not only problem, it is also an opportunity that we are really lacking a lot of energy. That and in energy is basically a representation of other different human requirements that will have to generate by 2050. So these are some of the stats. By 2050, the world population will grow by 47%. So today we are having about 7-8 billion people. The growth will be around 47% over the next 25 or 30 years. And more interestingly, 99% of the increase in this population will be from the development countries. So India, China, Africa, South American countries like this. And on an average, the population of Italy, which is like 60 million, will be added to the world every year. So these are really daunting numbers. And more than that, today we know that technology, which is slowly emerging in different aspects of life, practically have now covered all aspects of our life. Technology will play a homogenization role, which essentially means that per capita input or output will be basically same. Now, what do I mean by that? I mean, today, if you go to America or if you go to Africa or if you go to South America, you will see that maybe older generations not that accustomed with that information technology age, but you will see the younger people, they all are using the same apps, same Facebook, same WhatsApp that we are using in India or in the US or any other countries. So as this population come to the workforce, they will have the same dream, same aspect of life, same concept of life, and this will be a huge homogenization. They will also ask for the same same access of jobs, security, and lifestyle that we have. So actually, we have a huge challenge in front of us, just because this population growth, for this 47% growth, which is going to happen over the next 30 to 35 years. And these challenges are, as I said, but more clearly written here: population growth and sustainable development, energy security, climate change, disease and global pandemic. Well, we now know from last year what that means. Well, no need to explain anymore. But at the same time, we need to have clean water, healthy food, and that basically all of this led to economic development, and that is basically national security. So when when the planners for countries sit to discuss what are the national security, these are the first and most important things they need to discuss, or they discuss for the betterment of the country. Now, just to give you an example of different aspects of these challenges. So, this is a diagram of how much energy consumption was there in 2003, and how much energy consumption need to be there if you have to keep the same societal progress by 2050. And as you can see, as we spend the fossil fuels, oil, coal, gas, their contribution to the total energy has to be will go down, because they are a finite number of present in the world, and a huge amount of energy, about 20, 13 to 14 terawatts of energy, then you have to generate from renewable sources. And this renewable sources not only has to be sustainable, they also has to be affordable, and they has to be clean. So in terms of the scientific development, these things it is not only necessary to create these clean, affordable energy technologies with scientific mind, but it also gives a huge business opportunity for all of us. So while we create these energy sources or energy uh, mm, related energy security, we also have to be mindful about its environmental impact. We just can't create many coal-fired power plants; it pollutes, and in US is leads, China is behind it. We are also not. We are also number 4. So while we create these energy sources, we also have to be very careful that we don't pollute the environment. We need to reduce the CO2 emission rate, and there will be a talk which specifically direct how to address this CO2 emission. It's a major concern today. And sustainable development, that also means a clean development. And finally, if you look at peace and stability around the world, most of the times the conflict zones in the world that you see are basically fight for these different basic requirements like water, electricity, jobs. And if you look at different conflict zones categorized by different colors, most of them are actually for these fundamental things only. There could be some other reason for fight also. Probably those things will continue as long as civilization continues. But if we can address this, some basic principles or basic jobs, food, safety, some of these conflict zones, we can solve it by itself. So basically, uninterrupted supply of energy, foods, and jobs can lead to sustainable development. Now, it looks like a daunting challenge, but is it the first time the world has seen the challenge? No. The answer is no. So I'll give you 3 examples where the world faced an enormous challenge over the last 200 years, and the scientists and engineers have come up with a solution. So the first challenge was around 1800s, late 1800s, where the world population had started to grow, and there was a huge food shortage. And the answer of that came basically from this ammonia synthesis process, because ammonia is used in the fertilizer for massive food production. So these 2 scientists, Haber and Bosch, created this process called Bosch process, where nitrogen and hydrogen are added together with catalyst and temperature to create ammonia. And that really changed the agriculture industry. That not only changed the agriculture industry, it created a food security for billions of people around the world, and basically sustained this population development. Fortunately for this process and many other scientists' work, today we don't see the massive famines, which used to be a normal case. Many of the countries like us around 50 or 60 years before also. The second example that we see is a development of penicillin. Now, we all know bacterial diseases, and there was this bacterial disease which was killing millions of people until Alexander Fleming created this penicillin, and that saved millions of lives for infectious diseases. That also sustained the development of population and development of growth for many years. Thirdly, and more not in any sense less important, is of course the development of transistor. Today we live in an information technology age, but many of you would know that transistor was actually developed just before the Second World War, and it was funded by the War Department in the US for communication with frontline troops from the American their basic command. Today, of course, transistor has percolated almost every aspect of our life, and it has also changed the way we behave, the way we talk, the way we live our lives. So the point of this slide is that in the last 100 or 150 years, there were many occasions, at least 3 occasions, where the scientists, the technologists in the world faced enormous challenge, and they have come up with a solution. Now, of course, in today's world, what we have seen in the last year, one example would easily be the COVID-19, and the development of vaccine could easily be termed or be put into this chart. So scientists and technologists also have to find some other solution as well. Now, one of the ways scientists and technologists look for solution is by nanotechnology. Now, one thing you need to remember is that nanotechnology is the vehicle. It's not the destination. It is through which you reach the ultimate objective of energy security or food security and things like that. Now, I'm pretty sure most of you have already seen this nano. What is nano? So if you really look at size from meter to millimeter like bees, and then micrometer, which are the red blood cells, and eventually 1 billionth of the scale will reach you to these nano sizes. And today's technology are all basically done in nano sizes. For example, the transistors are in the nano size range. The carbon nanotube, which is used for research, is in the nano size range. And then, of course, you go down, you get atoms. So nanotechnology is the vehicle today to drive these societal changes. And of course, many of you have seen this entire field being developed after the famous talk by Professor Richard Feynman that there are plenty of room at the bottom. Now, what are the questions that the nanotechnologists ask today to address this challenge? Now, I'll just list few of them, and these are questions which are open. So which essentially means that if you join a research program as a master student, as a PhD student, it's highly likely that you will be working on any of these questions. So for example, nanotechnologists today ask the questions how to develop batteries that charge instantly and contain high charge density. You think about this electric vehicle that are particularly exactly run with a battery. So of course, those has to be charged instantly. Otherwise, you used to sit there, to travel somewhere and to sit there, and then it has to have large charge density because you need a large mileage out of this. The second thing that people look at is how to mimic natural photosynthesis. Natural photosynthesis, as we know, is one of the most efficient processes of nature. So scientists are trying to develop a process in the lab which mimics that. This is one example. The third example could be how to create a better catalysis material. Now, catalysis is not only the ammonia production, catalysis could be production of anything. For example, oxygen reduction reaction, oxygen evolution reaction, hydrogen evolution reaction, things like that. Then there are how to make efficient light emitting materials so that our lighting in our rooms, in our outside becomes more energy efficient and better. How to develop sensors that monitor external and internal environments, and then how to develop drugs for COVID or vaccines for COVID, cancer, and other diseases. So most of the nanotechnologists really try to address questions which for some way either of this that are put in, or maybe some other also. But point is they try to address questions which really human kind faces today. So now, in universities and research programs, we categorize these questions into 3 aspects mostly. So one question is, of course, is energy and environment. The other question is electronics and information technology. The third is health and wellness. For example, if you join PhD program in Jncasr or any other reputed Indian or American institution or any other institution in the world, mostly will address one of these 3. For example, if you work on energy and environment, mostly you will work on either solar energy conversion, thermoelectric materials, fuel cell materials, battery, or catalysis. The primary objective will be to look for alternative clean energy sources which are long lasting and sustainable. Similarly, if you work on electronic and information technology, you'll probably work on better transistors, how to make transistor more energy efficient, how to make light emitting materials more energy efficient, sensors, actuator, interconnects. So that's a separate field by itself together. Not to say that you'll be in the same materials or electrical or physics or chemistry department, but you'll be working on any of this. And finally, of course, you will work on bio-related or health or wellness related uh, stuffs, which are like biomaterials, drug delivery, vaccine, disease, and then biosensors and things like that. So these are the different categorization that we see around the academic programs. So in our research, and not only in our research, there is a whole set of groups in Jncasr who research on energy conversion, energy materials. So one of the energy related work goes on basically to convert solar energy. Now, as we know, the sun is shining, and that comes with a lot of power. So the idea is basically to convert the sun's energy into some electrical energy, and that's what we do here also in JCSR. So here what you see is typically sun spectrum, which really spans from around 300 nanometer to about 2500 nanometer. So what we do in our research here is basically create these different devices. It's known as photovoltaic devices, which are the old technology in silicon photovoltaic devices you see in rooftops. But to increase efficiency, we also work on different other photovoltaic technologies like solar thermophotovoltaics, solar thermoelectrics, solar thermal generation, photocatalysis, and etc. So this is a major thrust in research, nanotechnology, and science today. An idea, as I said, is basically to create high performance solar photovoltaic materials. Similarly, in energy technology, we work on other aspects. For example, how to convert waste heat into electric power. If you really look at any internal combustion engines, for example, a car engine, or if you look at a laptop also, you all know that it heats up very much. And a major portion of the power that you spend through fuel actually goes to not only as a waste heat, but a major portion also goes away to create a coolant, basically to cool this device. Otherwise, they'll fail immediately. So the question that we try to answer is that can we create materials which will convert some portion of the heat into electricity? So that has been a major research thrust both in JCSR and outside, and something that can really give a lot of energy saving in many aspects of devices or in many aspects of life. Third, I'll just show you one example of this nano electronics. So because of time constraint, let me not go into much detail, but if you really look at circuits in your cell phone, not the transistor, but the circuits, they operate at a working voltage, their noise level is about 1 millivolt. But if you really look at how much energy that a transistor costs, it's of the order of volts, basically, about millivolts, as you see here, from from old days to 2.5 volt to new days 0.8, 0.7, zero point 0.8 volt. So it has reduced by some amount, but it has really saturated by zero point 0.8 volt or 800 millivolt, or 700 millivolt, or 800 millivolt. So the question is, the transistors operate at 800 millivolt, but the noise level is at 1 millivolt. So basically, we are spending about a million times more power, because power is square of the voltage. So we are spending about a million times more power. So if we can create voltage switches, transistor is basically a switch which operates at low voltage, that could also save us a lot of energy in our daily life, because we charge our cell phone and that costs money. We charge our laptop and that costs money, and that takes away a lot of power as well. So that is one of the research thrust that is going on around the world, how to create the next switch or the next transistor which operates at much lower operating voltage. So these are the grand challenges of nanotechnology, the big problems. But when you really come to solve them, so you visit any good any universities, So if you visit any university, you will look for different tools that people use to address some of these challenges. So first of all, as you are in nano regime, which is the smallest of about 1,000 times smaller than a human hair, you realize that pureness and cleanness is a major and a very important aspect. So that's why most of this nano structure growth takes place in pressure which are almost same as in the atmospheric pressure or when go out in the space. So the space is around 10 to the power minus 12 to 15 torr, depending on how close you are to a planet or an object in there. Whereas we create pressure in our chambers like known as molecular beam epitaxis system, which is 10 to the power minus 11 torr. So ambient, normal room temperature is 765 torr. Extremely low pressure, clean environment. For example, we make gallium nitride nanostructure for LED light emitting diode applications. So look at the purity of gallium we use, 99.99999. So we call it 7-9 pure, 6-9 pure gallium and nitrogen. And then we create an environment which is almost resembles like that of a space to create these nanostructures. So creating the nanostructure itself is a major challenge in an environment which is perfectly free from dust, which is perfectly free from any impurities and things like that. The second thing is that once you have created these nanostructures, also we need to visualize them. So in an light microscopy that you have used in the high school, because you use light, resolution is limited by say micron or two. Now that is still 1,000 times more higher than a nano size objects. So what you do, you cannot use light microscope. Instead, you have to use electron microscope, where you see structures through electron and look at how big an electron microscope look like. So this is just one floor, and you have to cut a floor basically to take it to the second floor, because that big a microscope, about 15 to 20 feet, a whole building, a whole room. In most places, a whole building are dedicated for this microscopes, electron microscope, with which you reach resolutions which are less than an angstrom, so even lesser than a nanometer, and you can basically peer through atoms with this type of microscope basically here. So if you visit some of our labs in Jncasr or on some other place, you can see this type of microscope and how people are creating or looking at their nanostructures with this. And with these nanostructures, you can basically look at atoms. For example, here I just showed you, what I showed you is something known as a super lattice. So all these dots that you see here are basically column of atoms. Instead of just one atom, these are column of atoms. You have precision of an atomic level. You know what atom is sitting on top of what atom. To that extent, you can go with today's microscopy technology. So not only that, once you have created these nanostructures and you have looked it into with microscope, you also have to make devices. And synthesis or fabrication of devices require combining different aspects of the devices together, different tools together, different nuts and bolts together, and that also you have to do in a very clean environment, because otherwise your dust particle or any impurity will come and sit on your device, which will basically destroy. And for that, today's nanotechnologists do this, prepare these devices inside something known as clean room. So the purity of the clean room is today is defined by how many particles you have, dust particles, unwanted particles you have per cubic feet. And in most advanced places today, you have clean rooms which can operate with 1 or 10 dust particles per cubic feet. In JNCSR, we also have a clean room where we can go up to 100 dust particles, quite about 100 dust particles per cubic feet. So you have to basically put covers on your whole body and put mask, so that even your hair, you realize even your hair can also become a dust particle and destroy it. So you have to cover yourself with everything. Finally, and with this basically you create this transistor. So wherever the foundries are there, where your transistors are made for your cell phone or for your laptop, these are the big transistors, these are the big 16-inch or 12-inch wafers they use to create this transistor. And then, of course, they cut it. And each of these wafers basically now fit in about 50 billion transistors. So think about when the first transistor was made, it was microscope. Just put some contacts on germanium with metal contact. Today's transistors are, of course, as small as 7 nanometer. And the price of the transistor, because they have so many numbers, have basically gone to a nano dollar from about
Hello, sir. I will not clear,
10,
sir.
10 tens of dollars to about nano dollar. So enormous progress have taken place on this. So with this, I'll just show you one of the world's most efficient switches. I told you today's switches costs about 700, 800 millivolt of energy, where the noise level is about 1 volt. So we have been able to create switches which operates at 60 or 80 millivolt range, as you see in this case. Of course, in this presentation, I cannot go details about it, but that's what not only we, but many groups around the world are working to create the switches of the next generation. And finally, before I end, let me show you also an aspect of nanoscience and nanotechnology that is global in nature. So you see, many of this characterization, because we work on nano field, required very advanced instrumentation and technology development. So there are these places called synchrotron, which are basically electrons revolving around circular paths to give you very high energy. And if you can go to very high energy, then you can look at very small length scale because of this uncertainty principle. So there are many synchrotron facilities around the world. For example, you around the world, where you can take your sample, take your material, and take your device to look at structural properties of the material. You can look at the electronic properties of the material. You can look at magnetic and thermal properties of a material. I just give you some example from my own research and from others also. And these are the places where you can go. All you have to do, you don't have to spend any of your money. If you have an interesting idea, if you have an interesting material, if you are interested, government will support you to travel to these places to do this measurement. For example, this is an example of a place known as ALS. I was fortunately there as a student, Advanced Light Source in Berkeley. Then there is a place known as in Petra in Germany, where a lot of people do a lot of cool measurements. Some other instruments. This is in if this is Spring 8 in Japan, which is also one of the finest synchrotron sources. And of course, there is also in Brazil also. In India also, we have one which is in Indore, a place known as RRCAT, Raja Ramana Center for Advanced Technologies. So science synchrotron has really become a global project. So let me end, because I have come to the end of my time. Now, let me again go. I started this slide with a picture. So let me end with a big picture also, and really ask the question: in last 100 or 150 years, what are the major development have taken place? We don't really always appreciate this thing, so I just thought it was better to just put it. For example, among many of the great advancement, artificial fertilizers, which I showed, which is basically the development of ammonia, green revolution, antibiotics, electricity, airplane, transistor, nuclear energy, integrated circuit, polio vaccination, and now COVID-19 vaccination also. I think they should really start putting it in, because this is also something that is getting slowly in us, how major that event was of the last year. Uh, but the point is that over the last 100 years, there were so many major achievements, major development has taken place, and these are the leaders, these are the people who have developed this. And if you look at their names or their figures, they span from everywhere. Not only they span from university officers, students, but they all come from industries, technology pioneers, in many aspects of life. So it's not necessary that you only have to be at this place or that place. You can contribute basically from wherever you are into this. So just think about the case for the next 50 years or next 100 years, the great discovery that yet to happen. And I'm pretty sure many of in the schools or in the colleges will be the forefront of this development. So I'll stop, and then I'll be happy to take any questions that you may have. Thank you.
Google Meet questions. You can post your questions now on either Google Meet or YouTube chat box. We'll just wait for
Sure.
5 seconds.
No problem.
Okay, I think we will. Yes, please ask. If you have any questions, you can please go ahead. There is one question from Monojit Chatterjee. Can fusion energy be the best solution for us?
Okay, so can nuclear energy basically, I'll just generalize it to say that can nuclear energy be the best solution for us? Yeah, that's a very important question, and that's a question which is highly debated around the world. So, the nuclear energy is, in some sense, the cleanest form of energy because it doesn't create any greenhouse gas or any CO2 gas emission. But it does come with a major safety issues also, as highlighted by Fukushima in Japan's case. So, and answer of this question sometimes is very difficult even for even for those who are in the policy making, because everyone wants nuclear energy, but I'm pretty sure no one wants a nuclear power plant next to their home. So I think, and my own view is that we should definitely go for nuclear energy, provided some safety standards can be maintained. And safety standard is this nuclear facility should be isolated from uh, large population interdensity places. Proper safety should be always in mind. Then I don't see why you should not go for it. Actually, we should go for it, given the cleanness of these technologies. So it is definitely a solution, provided appropriate safety measures are taken.
Thank you, Dr. Bivas. So, in the interest of time, we will unfortunately have to cut short this and not take forward in discussion. But let's thank Dr. Bivas once again for this very nice talk.
Thank you.
ಅಲ್ಲೇ ಇಂಟ್ರೊಡ್ಯೂಸ್
Okay, so the next talk is by Professor Sebastian Peter. So let me introduce him briefly. He did his bachelor's and master's from St. Thomas College in Calicut, Kerala, and did his MTech from the Cochin University of Science and Technology. Then he went to Germany for a PhD at the Institute for Inorganic and Analytical Chemistry, University of Münster, Germany. Finished that in 2006 and then went for postdoctoral fellowship at the Max Planck Institute for Chemistry and Physics of Solids in Dresden, Germany again. And then did a second postdoctoral fellowship at the Northwestern University, USA, completed that in 2010, and then joined JNCSR. He has won several awards and several recognitions for his work, including the ACS Award, MRSI Medal, Emerging Investigator, sorry, and he has also initiated a startup called the BREATHE Applied Sciences, which basically aims to convert carbon dioxide, which is a greenhouse gas, into a usable fuel. He has also won the Swarnjyoti Award in 2017. But today we are here to hear about his amazing journey, which is this BREATHE Applied Sciences, which is a startup that he has initiated. He, along with two other team members, one is Professor Umesh Wagmare from JNCSR and a former student of JNCSR, Mr. Rakshit, Dr. Rakshit. So let's hear the story. Dr. Sebastian.
Thank you very much. So good morning, everyone. First of all, I would like to thank Jncasr and CNR Hub Science and Education Technology Unit and Fellowship and Extension for giving me this opportunity to share the journey of my startup, how we started, what are the struggles we had, what are the success, what are the achievements, and what we are looking forward. The startup name is BREATHE-inception Sciences Private Limited. The aim of the startup is translating an economic decarbonization. So this is a fundamental science, how that can be transferred technology. This is a key part I had to go through last 5 years. Before beginning my talk, I wish all everyone uh, uh, a very happy National Science Day. So the theme of this Science Day, so nothing but as mentioned, Professor Vidhyadhiraja, future of STI, impact of education skills and work. So my talk, I will direct in that direction. Was not there.
There is some phase lag, time lag. It will come. It will come.
It was not there before.
Now it becomes.
Sorry for the interruption. So, some technical problem. So I just go back and wish you all happy National Science Day. The theme of this Science Day is Future of STI, Impact of Education Skills and Work. So I take my talk in that direction today. So the mission and vision of the startup is nothing but it is a technology startup to provide commercially viable and scalable technological solutions to the problems due to anthropogenic CO2. CO2 can be produced by various sources. It can be man-made, it can be natural, and due to the industrial revolutions and urbanizations, etc., over a period of last several centuries, there are several strategies tackle this issue. And you can see that, as a chemist, chemistry point of view, you can say that when CO2 can be converted, all the chemicals can think about it. As per the literature, there are 123 different reaction pathways CO2 can take into the product. And it is extremely, difficult to tackle which pathway we have to follow. I just want to take you on the issue. As of today, 28th February 2021, the average CO2 level in the atmosphere, it is 416.33. Every minute you can get this number. If you go CO2.earth and the rest certain observatory, and you can get this number. So it depends on the different the calculations, you can get that one. So what it actually shows. So you can see that last 1 decade it started from 390, now it is 416. It is actually going up and up, never going down, and it can reach 450, 500. And it introduced a lot of issues. For example, global warming. You all are familiar to this one. We got a beautiful nature, but we made the nature in such a way, and we are living dangerously. And you can see that it's not only affecting the local, and each individual that get affected. Depends on whether it is 1%, 2%, 5%, 8%. It can affect your the health systems dramatically. Not only that one. So there are reports from IPCC by 2030, 2040, many cities in the world can be underwater because of ice melting. These are all coming from a symbol as the molecule carbon dioxide. This is produced in any, organic reactions you can think about, where carbon is actually react with oxygen and is forming oxide, carbon dioxide. So how we started? I'm not going to the science much detail because of the time limit, but I go the glimpse of that one, how we started. The journey started way back in 2014. I got attracted to this beautiful paper published in Nature Chemistry, group of Nosko and team. And what he has done, he discovered this catalyst nickel gallium based intermetallic for the conversion of CO2 to ethanol. It's a combination of theory and experimental. I am a material scientist. I found of analyze intermetallics over a period of last 15 years. I got an attraction to this one. Based on this, I wrote a proposal in collaboration with Professor Umesh Vakmare way back in September 2015. And DST, kindly provided generous fund to start the fundamental chemistry. So we started to dig out the materials that can be potential for this in application. And we published a few papers, and one such paper published a month back. This is it's ACS Energy Letter, one of the high-profile journal, CO2 to methanol at low pressure. So energy is one of the concern. So not going to the detail, and just go back again 2016. So we published a lot of papers. As an academicians, we published 20 papers, 30 papers. But the point is actually how many papers we can translate in real application. Because we are not in the culture, we are not well equipped with that one, and these are the hurdles actually everybody is facing, including me. So what we have done, we got good opportunity to interact with the industry people in 2016, the first academic industry meeting held at Jncasr. In that meeting, Dr. Rakshit Bellu, he is an engineer in Airspace Bangalore, so he came forward. He actually got an attention to this energy quasi carbon X prize, $20 million X prize, and he proposed a lot of challenges on how to capture CO2 from power generation sectors like natural gas and coal, and how we can convert to anything you can think about. So he came forward. He got in touch with Umesh Vakmare, and then they are looking for the team to participate in this one. So they have left and right discussions on this one. And then at that time, me and Professor Vakmare started this DS in animation. And then, just immediately he just, introduced me to Rashid. So then we started the team in 2016. Now, there was actually short, time for the submission of the proposal, 4 days. So the question is that guidelines 100 pages, who will read it? And this is completely new to me. I took almost 10 days to digest and decide whether I should go for that one, because it is a big journey. So a lot of questions arose at the time: the time, money, team, manpower, technical challenge, etc. and etc. And you are talking about $20 million price. And then finally I took a decision. Yes, one life, one challenge, take it. If you are successful, it is successful, and then go ahead. So we took this one, and I wrote the proposal 4 days continuously. To be honest, almost no sleep, 4 days continuously, submitted the proposal. And the industry party for the registration, $1,000 just for the competition. Thanks to Jncasr, and always go to Jncasr. So every support is always there. And we got the money, as I told NSA, this money is issue. So we initiated. So the question starts. I am an academician, so a foot into words. As an academic entrepreneur, so he has to actually hold both sides. So he has to hold the traditional scientist, he has to hold the traditional entrepreneur. So that was not used to me at the time. I never thought about, okay, I will go to this, this translation, but this particular subject was quite interesting. So then I was looking around the world who is actually successful. This great gentleman, George Whitesides, Harvard University, he has 12 companies, and he is a director of 17 companies, including his startup, 12 startup. Amazing to see that one. It's not only a director, his agenda is 230, citation 2 lakhs plus. Whatever you can think about, everything is on the top of the world. So yeah, this is global. We have different culture, different things, and everything there. But I just try to identify who is actually in India. You can see the Professor Pradeep and IIT Madras. He has 5 startups, and then H-index is 75. This all inspired me. Okay, why not me? I am only, when at that time 38 years old. So fine, I will start that one. And if others can do, why not me? So then the another inspiration I got, Team Indus Moonshot. There is a another express competition, Google Lunar Express competition, soft landing of the space shuttle at the surface of the moon. That was the theme, and this team is actually only 3 kilometers from Jncasr. I visited this team on regular basis to understand what are the struggles. They had gone through. At that time, they were in the final. It was not easy. They also expressed so many things, and then I tried to learn. Then how we can tackle, starting from the the investment, financial thing, and the time and infrastructure, everything you can think about, the connection, network, etc., etc. So, but their journey actually inspired me. And then another one inspiration. There is a plant, developed by Professor George. He is Nobel Prize winner for his, enormous, contributions in the field of carbonate chemistry in 1991. And his, student, Surya Prakash, he is a Bangalorean, and he is advisor to this Nidhi Aayog. And here they started a plant in Iceland with a capacity of 4,000 tons of methanol per year. They started the journey in 2007. And then, they just, you can see that they started actually 2007. And the first, products actually happened something around 2015. And this still, if you talk about technology readiness level, it was actually technology readiness level something around 7 to 8. It is not completed. What the good part actually, the energy they use is geothermal energy. Unfortunately, it is geographically restricted because the cost associated with the energy is different at different parts of the world. There are so many other companies like Gas in Korea. They produce DME, dimethyl ether. They also started in the period of 2005. And what is a beautiful part of this company, they also produce 300 kiloton of dimethyl ether in Korea, and that can be used as energy fuel in every sector. They are constructing 4 plants in the Middle East at the moment. So this all inspired me. So we will also start from here. So we proposed this technology, and in the paper it looks so complicated. I don't want to go there. I will take another slide to explain this one. In this proposal, we proposed and then registered, and there were actually around 47 teams in the first round. And in 2016, October 16, and we got a good news. We advanced into the final round of the competition, 27 teams. It was highlighted in Times of India and in the other leading journals. Okay, and the good part is actually we were the only Indian team in the semi-final round of this competition. It was a Times of India, ACS journal. It was in the Nature news. So many people left and right came forward, interviews. I became so busy. Okay. So many interviews. I also learned how to do. Stand in front of TV camera, etc. And all. Then started the problem. So we got in the final. We have to develop the technology. So all problem I end up in one person, Professor Rao, for the solution. So there was no space, no money, no manpower. He provided everything. And to be honest, he provided lab, and he provided this manpower, he provided instruments. My first reactor actually provided by Professor Rao from his hands. So I got all this. That was a good start from Professor Rao. And then it was enormously supported by Professor Vidhyadhiraja, who was the president at that time, the Jncasr, and Professor Jncasr, and he was an R&D and then in charge of PA of TRC, Technical Research Center. So were that fund coming for this translation research. I also got good amount of funding from TRC and Jncasr for developing technology. Then we had to go on through another, the tricky part. We had to go on through, a lot of legal things. Okay, so how to write, NDA, how to write an, MOU, how, so technical transfer, IP transfer, how to contact, how to read the lawyer's language, etc., and etc. Beyond science, in addition to the economic or business, etc. So I put on all effort actually to learn, but still I can say that when I have to learn a lot. Okay, so probably from zero I advanced to 10% or 15%, 20%, whatever, but I have to learn more. Whatever happens, JNC was very happy to accommodate BREATHE as an incubation, startup and a part of the Jncasr. And then I signed an agreement of BREATHE and Jncasr. And you can see that Professor Kulkarni, current president, Professor Chandras Narayana, D. Narandi, is director of Jivandi Center in Vandram, and there was, Dr. Professor Yamush Vakmare and Mr. Jaydeep there. So we signed this agreement, and then, so BREATHE is a baby of Jncasr, and Jncasr is a mother of BREATHE. So we work with that. And the team, so starting with the team from students, and slowly it's translated to the BREATHE embrace. So all the technology start from the student. To be honest, I got lucky to have, wonderful students, and their contribution was enormous. Started from Brother Roy, he's a postdoc there in US. This is a small number, this initial stage, but we have a lot of students actually helped this one. So now action. So we have taken the challenge, and as you see the challenges, it's complex reaction pathways. Hydrogen is the reactant using. So it's a safety component associated with that one. Not only safety, expensive, availability, etc. Selectivity, if you're looking for methanol, the selectivity may not be good. And then the reactor needs to be minimized, the engineering aspect. So, I learned, business, and I had to learn, I had to learn the chemical engineering. So one of our other problems actually, trying to tackle that slowly by slowly. So we introduced chemical engineers into the team to understand the process engineering and better. The chemists actually designed the catalyst using the fundamental concept of the chemistry. And this is a combination of the multi personalities, the different expertise in this area. So a single man cannot do this job. I just coordinate them and left and right. That's all I did. So with all his help, we started the process, and we designed this hundreds of catalysts. I can tell you, so hundreds of, maybe, it can be reached 1,000 also. So we had to test a lot of, the catalysts, the processing also. So different synthesis technology and processing, and here I'm not going to the details, so synthesis, this form, and then calcine, binder, etc. And the beautiful part actually, the best, advancement we did actually, we scaled up this synthesis. The one problem, limit or drawback of our country, we are still not established a manufacturing unit. Any chemical you can think about. We are still progressing, but a long way to go. So we had a discussion with the Johnson Matthey, etc. companies. They supply actually catalyst to the CRI plant Iceland I was talking about, but it was involved huge investment and IP transfer, etc. So why not we doing here at Jncasr? So we customize this synthesis unit, manufacture unit, processing unit, and we develop the catalyst in one shot. 5 kilogram catalyst can be synthesized in that unit. We can scale up in even higher level if you are looking for the last plant. So this is the first semi-final round of demonstration. And you can see that this is the first reactor, supported by processing and Rao with a capacity of 5 kilogram of CO2 per day. And you can see that this conversion, I'm showing only 2 slides, but it involves 3 years of research, to be honest. And this, you can see that on 45% of CO2 conversion, what the improvement we made as a team of Jncasr or BREATHE, here in Jncasr, it's nothing but, the commercial catalyst is 20 to 25% of conversion. We reached, 45% of conversion. With the selectivity, close to 90. The recent past, we reached to 93. And I just want to, inform you, yesterday we got the conversion close to 57. That is, latest, yesterday evening by 6 o'clock. So we are improving every day. And then you can see that when methanol is coming from the reactor, and it's a small scale. And the team from US and Southern Research, etc., they were here for 6 days to technically evaluate this technology. And based on that one, and we got a good news. We submitted a report, and we got a good news that we are in the final round of the competition.
Today, our planet heaven on its own. The Jncasr carbon export is a $20 million competition to convert carbon dioxide into valuable products.
Carbon technology takes CO2 and converts it into stronger and greener concrete. Our process makes a very nutritious protein.
Carbon emissions, carbon negative bioplastics and other sorts of materials. Carbon nanofibers, feast for fish. We take carbon dioxide and water, and we turn that into alcohol. You can drink it to make yourself feel better.
My motivation for competing in the Carbon X Prize is what am I going to leave for him? 50 years, 100 years,
There's a sense of the climate change and refused. That's in 2018 Superconductivity accepted challenge. After years of development testing, judges narrowed it down to these 10 finalists. Competition, teams must scale and demonstrate technologies and emissions from real power plants. The finals will take place at 2 test centers.
Thank you for watching. So it was a marvelous day. So we got the good news that we are in the final of the Jncasr Carbon X Prize, and you can see 10 teams at the podium on New York Grand Hyatt Hotel, and it was a memorable moment. So of course, I mean, we ended up the semi-final and final round. We got a lot of achievements, so we have been, selected as one of the, best startup by the Karnataka state government through the program Elevate 100 in the first section itself. ONGC selected as one of the best startup out of 2,700 applications. Clean Equity Monaco in 2019 selected as a second best startup in the field of environmental technology research. We got a lot of partners in left and right. A few are here. So many of them are engineering, many of them are partners, many of them are the support and evaluation, etc. And we were in actually major newspapers. So it goes on. Even once I visited, Southampton, and then they just put in the newspaper Carbon X Prize finalist Professor Sebastian is visiting university for today. So this kind of all the attention we got. But the problem is what next? So we got into the final. We had to prove that and why we got into the final. So the grand challenge is, as per the guidelines, we have to demonstrate 2,000 kilograms of CO2 per day, 2 tons per day capacity, plant at Wyoming, US. We got the land, we got the office, and I visited, a couple of times, arranged and everything. And we were actually, quizzing to get them financial support, investment. We got investment, promise. If you're going to US, everything we got it. All of a sudden, COVID-19 came into the picture. And then we were forced back actually, India to do this experiment because of the logistical issue associated with that one. Then we identified so many, partners involved in that one. So we got, Carbon Clean Solutions. So this is an Indian-based company started by a couple of guys from IIT Kharagpur. So they have 7 plants, across the globe for CO2 capture. We got support from, X Prize and Texor Manufacturing Mission Innovation, supported for the funding, TRC, and then BREATHE is a part, then major of this development. We have done the major support from TRC and Jncasr, and then as per the incubations, so we started operating at Jncasr. Initially, we planned to go to Tuticorin. There is a plant, CO2 capture plant is there, And then we about to go, all of a sudden, COVID regulation came, then COVID regulation removed, and then, of a sudden, hurricane came, and then, the plant was got broken, they repaired, and then workers started actually, protest because they did not have the salary at that time, blah, blah, blah. So many things have happened. So what we decided, okay, we'll capture from CO2 from Tuticorin and bring it here and do the experiment at our site. So we had developed a plan here, and then we just in the process of optimizing. This is our plan, and we are here to complete. But whatever the optimization period, we got, wonderful result. And I will go through this figure again. Earlier I showed this one, a sustainable circular carbon economy. That's what we have done here. So in 2017, we completed this due process, and then you can see that one. See, this is a 2018 CO2 reduction unit, and first 9. So we developed the methanol distillation unit. Phase 3, 2020. We started actually. Hydrogen generation unit, and phase 4, 21. It is going to be established Jncasr. And then we already have the partner 2020. So we just integrated in this unit with our unit. And phase 2, 2022, next year we are planning to deploy this on, the chemicals, one automobiles or fuel industry. That we are in discussion with various industry sectors in this area. And we're expecting the revenue start by 2022 or 2023, depends on how we progress. We don't know exactly, but our target is 2022. So we have done a lot of economic analysis. One small analysis here, as per the market, $482. Now it is increased to $493 per ton international market, and as per our technology, $302 per ton. That is what we calculated. As I said yesterday's calculation, it is gone down to 170. So we are actually going to have a methanol probably 12 rupees to 15 rupees liter per methanol price we are going to produce. As per the market is actually 25 to 30 rupees per liter. So we have a lot of business model, so we are taking as a turnkey project, combining all this one together. One such the project is getting into finalized, at the moment. Sale of chemicals, sale of catalysts, sale of carbon credits, etc. So, to be honest, I have to understand all this, although I know something, but long way to go. Future. So what is the future? As I said, we have a lot of industrial sectors. They are looking for, technology transfer or maybe as a partnership. And I just want to say that when DSC also generously, approved a Center of Excellence on CCU at the Jncasr. So we are working on that one. So this will help all the academicians, in the country can have a strong network, and we can mediate, your interactions between the different academician or different industrial sectors. They can come forward through the center, and then if you want to transfer your technology that, what we call the industry, you can turn through this center. That's what we are working on that one. We got the approval, we established, and we are actually in the process of setting it up. And finally, I conclude the journey is nothing but it is started, it is going on, it has to go, and we are, looking for 2030, 2040, 2050. I missed one point to mention our technology evaluated by many teams across the world. One such team, University of Calgary, life cycle analysis. This is one of the important analysis to make sure that technology is going to be profitable. Technology is going to be the beneficial for the humankind. So what they have done actually, economy aspect, and they have done the decarbonizations, and then for carbon negative, carbon positive. As per their the report, our technology is going to be carbon negative by 2035. So this is a good, a very positive report we got it. So I just come to here. So we take this the science through Jncasr, fundamental science, developing the material and methodology, understanding all the the scientific challenges and how to surpass those one by designing and process engineering, and you use a lot of experimental and theoretical knowledge to build a case. And then we take, whatever the promising technology translating through BREATHE, as I said, different model of a business plan. And finally, it can be good impact, social impact to India and the global as well. So we are actually kind of, so towards the in India and the clean India and the efficient in the energy India. So that is our theme of our process. And finally, May, June 2021, the winner will be announced. We may win, we may lose, we may be second or we may be third, we may be first, doesn't matter. We will go more forward. And because we have the technology, we have our own strategy to move forward. And finally, as Walt Disney says, all our dreams can come true if we have the courage to pursue them. Thank you very much. And I wish you a happy National Science Day once again. Thank you very much. Thank you.
Yeah, so it's really great to see the journey of BREATHE, and I do hope that you do win the express. Okay, this is all the best for you. Unfortunately, we don't have time for questions, and I'm sure there will be a lot of them because we have to go to the next part of the program. So let's thank you once again for coming here and spending your time here.
Thank you very much.
So the next item on the agenda is some experiments that I and Mr. Vinayak Pattar, who is at the Education Technology Unit, we will be conducting. And we'll be focusing on three main topics: optics, magnetism, and superconductivity. So very shortly you will see a range of experiments set up on the table, and I hope all of you can join. Live. So good morning, everyone. I hope you had a very nice time in the morning. You heard two talks by Dr. Bivas, Saha and Dr. Peter Sebastian. And both of these talks were, you could see they were focusing on a lot of energy problems and how solutions can be found for energy problems through nanotechnology, through catalysts and conversion of CO2 to methanol. So these are really burning problems, and the faculty of Jncasr are working really hard to solve these problems. So as part of the National Science Day, we have put together some experiments just to excite your mind and to ask questions and be curious about science. So let me start with light. Okay, and before we start with light, let me start with darkness. So why are we afraid of darkness, right? And if we had an audience here, I would have asked questions. Obviously, there is, the students were here, I would have asked questions. But in the absence of students, let me myself give the answer. So we are afraid of the dark because we can't see in the dark, right? There is a fear of the unknown, okay? And fear of the unknown goes away if there is light, right? So we can see around us and then figure out. So let's start with light, okay? And the properties of light, right? So what I have here in my hand is a handheld laser. And the laser itself is a very interesting object. It gives out very coherent and a very collimated beam of light, very intense beam of light. So today we have a green laser, so you can see this. And light itself you can't see, but whatever light falls on and then comes back to our eyes, we can see that, right? But can we see light itself? And it turns out, yes, you can see light through something that study in the 10th standard. It's called the Tyndall effect, right? So in the path of the light, if we can put in some dust particles or some other particles which can scatter light, and that light then comes into our eyes, then we can see the light beam, right? So let's try to see that first. Right. So we have here two tanks of water, right? In one tank there is clear water, it's just pure water, and in the other tank we have added a few drops of phenyl. Okay, and this is added because the phenyl molecules will be able to scatter light, and we will be able to see the beam more clearly. Okay, so if we shine here, then you can see that you can hardly see the beam inside the tank, right? So because there are no scatterers inside. Whereas if I do the same thing here, now you can see that the beam is clearly visible. Okay, so this is again just a manifestation of scattering of light. And you know, the National Science Day we are celebrating because of this is marking the discovery of the Raman effect. And the Raman scattering is again a very important scattering effect of light, where a single color goes in and then it interacts with the crystal structure, with the lattice, with lattice vibrations, and what comes out is slightly shifted color, okay, either upshifted or downshifted, right? And that is basically Raman effect. So that is also to do with light scattering. However, the scattering that we are seeing here is a slightly different kind of scattering. We can show Raman effect also. We have a spectrometer here, and if you visit JNC, we will take you to a building called the Chemistry Exposition Building, where we have a Raman spectrometer and we can show you the Raman effect. So today we are going to see Rayleigh scattering. And before we show Rayleigh scattering, let's look at one more effect which has enabled internet all over the world. Okay? And that effect is the total internal reflection, right? So we know that light, if you look at optics, geometric optics, then we know that light travels in a straight line. But light is both a wave and a particle, remember that, right? It has a dual nature. So in geometric optics, we study only the ray properties of light, the geometric properties of light. So if we see, do we have a mirror? So let me go directly into this, the total internal reflection. So basically we have here a medium which is outside the tank, which is air, and inside the tank we have water, right? And what we are going to do is to shine light which goes from within the water, right? And then, so let's do this. So we are making the solution a little bit dilute, right? So let me make the angle a little bit. So do you see the reflected light, right? Do you see the beam is getting internally reflected, right? And that's because there is no mirror here, right? And the beam is going up, it's going from a denser to a rarer medium, but then it has crossed critical angle, and because it has crossed a critical angle, the light is coming back into the denser medium and is getting reflected. Now this phenomenon, it's so easy to see, and we see it on a hot day also, on hot roads. When if you're traveling on a hot day and you look far ahead, you would see a kind of pool of water on the road. But when you go closer, you see that there is no pool of water. In fact, there cannot be because it's so hot, right? That's a mirage. And the same principle is being shown here. Now, this is not just a scientific curiosity. So, today we are using things called optical fibers, where inside the optical fiber, the phenomenon of total internal reflection is being heavily used. And the cell phones and the laptops that we all use, the internet that we are so heavily dependent on, actually uses internet based on optical fiber technology, which in turn uses the phenomenon of total internal reflection. Right? So it's not just academic curiosity, right? So this this entire concept has been taken all the way to technology, right? So let's also see the path of light. So Mr. Vinayak here uh, has an incense stick, right? And this incense stick provides the smoke. Light off. Exactly, that's what I was saying. So now we'll show you a slightly different phenomenon. So this is a compact disc. It's a CD or a DVD, and a CD or a DVD has many tracks here. Okay, these are not normally visible, but if you look under a microscope, you can see many tracks here, right? And it turns out the spacing between the tracks is roughly of the order of the wavelength of the light, of this laser light, right? So what we can do is, when we shine this light on this set of tracks, you can see this acts like a diffraction grating, and you will see a diffraction pattern. Okay, so we are going to do that. Now, when I normally do this, you cannot see the light beam, right? But if you look at the ceiling, you will not be able to look at it right now, because the camera cannot focus there. You can actually see many different patterns emerging. Okay, so maybe we can show it here. They can see? Okay, fine. Okay, so you can see this, right? But we can't see the light beam itself. So this is where I was mentioning that we can use the Tyndall effect to actually see the light beam. Okay, so Mr. Vinayak has a duster, and there is some chalk powder on it, and he is going to tap that. So let us see. So you can see the light beam so beautifully that there is one beam going in, but there are several beams coming out, right? And this is because the CD has several tracks on it, and that is actually diffracting the beam in different directions. Okay? And when you see the ceiling, actually you can also see interference pattern. Okay? Right. So now let's focus on one more question on which Sir C.V. Raman has written a whole article. Okay? And he wrote the article on why is the sky blue, right? So many people have tried to understand this question on why is sky blue, right? And if you study that in your 10th standard or maybe 11th, I think 12th standard probably. So here we have a small demonstration for that. So we'll see this, we'll see clear. So this is clear water, and what we are doing here is that we are shining white light. Now this is not a true sunlight. This is white light coming from an LED source, and the spectrum of this source is not the same as that of the sun. Okay, but still we can actually see this effect. Okay, so what we are doing here is that we are shining light through clear water, and because in clear water there are no scattering particles, you will actually see white light everywhere. Okay, it's a kind of bluish white light everywhere, right? But now what we'll do is, we have now a different tank, where in this tank we have added a few drops of phenyl, right? So what we should see is that when we shine white light from here, the white light goes in, and then the blue light, the blue component of the white light will get scattered the most, and the red light gets scattered the least, right? So as the light traverses this path, the initial part, the tank should appear blue, and the later part should appear red. Okay, so if you focus on this, then you will see that the initial part looks kind of bluish, and the final part, this last part here, looks kind of orange. Okay, and we can exaggerate this effect by adding one more drop of phenyl. So let's do that, and you will see that this effect gets better. Absolutely. So now you can see that it's the same white light, right? But on this side you see really orange color, and on this side you see blue color, right? And it's not that we have added any orange color, right? So because if I take this here, see, you can see that this is all translucent and whitish, right? But if I now take this here, again you will see the same thing. Okay, So you see a kind of orangish tinge here, and this is a bluish tinge. So this is telling you that white light is going in, the blue light gets scattered most, and the red light doesn't scatter as much, and then the red light is able to travel farther because it is getting scattered less, right? And this is the reason why the sky is blue during the day, and then during the sunset and the sunrise, the sky appears red, or the sun even appears red. Okay. Now there is a detailed explanation that we can go into. We can show you some figures, the sun rays, how they travel and they reach our eyes, but this is not much time here. Okay. And I would encourage as many of you as possible to come and visit JNC. You can just write to the fellowship and extension section from your school or college or your institution, and we will make the arrangements. Okay. All right. So let's move on to magnetism. Let's remove this. All right. So what we are going to do now is to find out how do trains apply brakes. Okay. Now you don't see a train here, you don't see brakes here. So you'll ask me why am I asking this question? Okay. And the effect that I'm going to show you is actually used in designing brakes for trains. Now trains are very heavy objects. It takes a lot of force to stop them, right? So the effect that I'm going to show you must be very powerful, right? So what I have here in my hand are two copper pipes, okay, and we make this so that we can carry them everywhere, but we can join them, right? So we have the copper pipe, and we also have a plastic pipe. So let's take this is fine. Yeah. So this is a PC pipe, and this is a copper pipe. Okay. So what we are going to do is to drop. So these are magnets, right? And we're going to drop the magnet through this PVC pipe. And what do you expect? It should obey Newton's laws, right? So if you write down the Newton's equations, that the u is 0, right? And there is a certain length it has to travel. There is an acceleration due to gravity, g equal to 9.8 meters per second squared. If you do all that math, you will be able to find out how much time it takes for this magnet to travel this length. Okay, that's very simple, right? Now let's do the same thing with this copper pipe. Okay. And yeah, this is a slightly longer one. This is about a meter long. And if you do the same experiment, and I'm dropping magnets here, and Mr. Vinayak is going to hold this. So can you focus on this part, Dilip? On this part. So the point is, we need to find out how much time it takes for the magnet to drop through this pipe. Okay. So I'm going to drop this now. 1, 2, 3. Okay. So it took almost about 2 to 3 seconds, right? So we have measured this, and now we have another magnet. Okay. So you see, it took almost 4 seconds. Okay. Now the question is that these magnets, when they fell through the PVC pipe, took almost no time. It took about 0.4 to 0.5 seconds. Okay. But it took almost 10 times the time for the same magnets to fall through the copper pipe. Now, is copper magnetic? So you can see it's actually not magnetic, right? It doesn't stick. So it's not as if the magnet is pulling the other magnet and then leading to an increase in time. Okay. So what is happening here? And again, if this was interactive, we would have actually asked the question and guide the students to give the answer, right? So what is happening here is an example of electromagnetic induction. Okay. So an electromagnetic induction is a very general principle. It's an extremely technologically useful principle. Electromagnetic induction is used in generators, it's used in motors, and obviously just these two are a really integral part of our lives. Okay, and as I told you in the very beginning, this particular effect that I'm showing you is an example of Lenz's law. Okay, and this law is used for designing brakes for trains, right? Why is that? So what is happening here is that when I'm dropping this magnet, the magnetic field lines of this magnet is cutting the copper pipe, and as the flux through this is changing, what is happening is there is an EMF that is generated, and that EMF is producing a magnetic field that is opposite in polarity to the incoming magnetic field. Okay, and that is causing the magnet to almost float in air. In fact, we have seen that this magnet reaches terminal velocity really soon. Normally, when you have a non-magnetic object which falls in space, you know that it accelerates due to gravity, and that acceleration due to gravity is 9.8 meter per second squared. However, this Lenz's law is so powerful that it is able to hold the weight of this, right? And instead of accelerating, this magnet in fact falls at a terminal velocity within about a few centimeters. Okay, so it's a really powerful effect. Okay, and I'm holding this, but I don't feel the current. Okay, not that I can feel the eddy currents that are coming. And this principle, you can see how it can be designed to, how it can be used to design the brake train, right? Because remember, the wheels of the train are actually made of metal, right? And if you can have a magnet which is attached to the chassis of the train, then you can design the brakes to act in such a way that they stop the really massive train. Okay, so this is an example of Lenz's, and in general, it's a part of electromagnetic induction theory, which is extremely technologically useful. Okay. So we have a lot of experiments here to demonstrate about electrostatics, about electromagnetism. We have a very simple DC motor to demonstrate. Unfortunately, we cannot go into all of that, and again, after every experiment, I will encourage all of you to come here, visit us, and enjoy with us. So the last experiment in this session is superconductivity. So let me first explain what is superconductivity, and then I will demonstrate that. Okay. So superconductivity is a phenomenon where a material, when is cooled down below a certain temperature, loses all its electrical resistance. So normally when we take any metal and we pass current through it, then there is Ohm's law, which tells us that the potential drop across the metal is proportional to current, and the proportionality constant is the resistance. In a superconductor, however, there is absolutely no resistance below the transition temperature of the superconductor. Okay. Now, this was discovered way back in 1911. When an experiment was being done on mercury, and the temperature below which it was cooled was 4.2 Kelvin to achieve the superconducting state. Okay. And the superconducting state is a very fascinating state. In fact, what happens inside a superconductor is so fascinating that it is actually unbelievable. So imagine that you have two like charges. And what we are told in the textbook is that two like charges should actually repel. So electrons inside a metal should actually repel each other, and that is what actually happens in any normal material. But below the superconducting transition temperature, what actually happens is that these electrons, which normally repel, start to have a finite attraction towards each other. Now, this is not normally possible. This attraction between electrons is given rise to by something called phonons, which are nothing but the vibrations of the crystal within which these electrons are moving. Okay? So these vibrations actually mediate the interaction between the electrons and lead to something called a Cooper pair. Okay? These electrons, they form pairs called Cooper pairs, and these Cooper pairs turn out to have very strange quantum mechanical properties called entanglement, and that is the reason we can move through this system without any scattering at all, without any resistance, which is what leads to the superconducting state. But there is something else about a superconductor that is also very interesting. okay, and that is called diamagnetism. And the effect associated with this is called the Meissner effect, right? So today we have a demonstration of this Meissner effect, where the superconductor, at least the type 1 superconductor of the mercury type or the niobium type, they happen to expel all magnetic field which is in which they are placed. Okay. So they can expel all magnetic field, right? Because there are surface currents that are generated, and those surface currents can actually cancel out any external magnetic field. Okay. So for doing this experiment, what we have are three main ingredients. Okay. One is there is a superconductor, and this superconductor is called ytterbium barium copper oxide, YbCO. Okay, and I don't know if it is possible to see this, but there is a small black disc inside this. Okay, this is a thermocol boat that we have built, and inside that you will see a small black disc. Okay, and that black disc is actually a ceramic. Now, most of you might be thinking a ceramic is a really good insulator, right? So it turns out this ceramic is very, very special. Okay, and if you cool it below the liquid nitrogen temperature, it becomes a superconductor. In fact, you don't even need to go below liquid nitrogen. Okay, you need to go up to about 90 Kelvin to make this a superconductor, right? So we have here a liquid nitrogen tank, and liquid nitrogen itself is a very fascinating object, right? So it becomes nitrogen becomes liquid at 77 Kelvin, which is about minus 196 degrees Celsius, right? It's very, very cold. There is nowhere on Earth which is that cold. The closest we come to that temperature naturally is on the moon in one of the craters. So this is the first ingredient, that is a ceramic, YbCO. The second ingredient is liquid nitrogen, right? And can we drop it and show liquid nitrogen this here? And it's a very dangerous object as well. Okay, if it falls on your hand, it can burn your hand. It can give you cold burns, right? The third ingredient in this experiment is this. Okay? This is a magnetic track. What this means is that we have magnets which are placed here on a track, okay, and the end magnets are placed in a slightly different, in a perpendicular way. And there are three tracks of magnets that you see here. The polarity of these magnets has been chosen very carefully to allow quantum locking of the superconductor. Now, what is the application of this? So, what we want to demonstrate here is the magnetic levitation train principle. Okay, so this track has a magnetic field of its own. Okay, and we have designed the track in such a way that it can produce quantum locking of the superconductor, right? So now what we are going to do is that we are going to cool the superconductor by pouring liquid nitrogen in the boat. Okay, and then we are going to release this on the track once it cools down. Okay, so let's see. So you can see how it is floating, right? And we didn't have to push it back. There was an automatic brake at the end of the track. And you see there are no side walls. Okay, it's not that the thing is very balancing, very delicate balancing. No, there is no delicate balancing here. What is actually happening is that the magnetic field lines are actually going around it, and it's actually locking the superconductor. Okay, so this is called quantum locking, and this is the reason why we don't have to provide any side walls so that it doesn't escape or anything. Okay, and this superconductor is actually levitating. Okay, so this is called magnetic levitation, right? And let's see if we can show you the best part of quantum locking. You do one thing, you cool it. So we are going to cool it once again and then show you. So it turns out China has already built a superconductor based magnetic levitation train which runs at 650 kilometers per hour. That's huge. Yeah, it needs to be, but I think it's a commercial train. They have brought it into. Of course, yeah. Yeah, if you're doing engineering, you know the scaling up process very well. This is lab, right? Correct. Yeah. Okay. Sorry, we need slightly specialized equipment to show you locking, but what we have shown in the past is that this thing can be locked by inverting the track, and the superconductor is able to float below this without any support. Okay, so that actually shows you that this is not a delicate balancing act of the superconductor. The magnetic field lines are going around it and actually locking the superconductor in place. Okay. So this brings us to the end of the session, but then we have a few more experiments, and the first thing we will show you is again something related to electromagnetic induction. So this is one example of a very simple DC motor that you guys can also make at your home. So what this has is one battery, okay, double A battery. These these are disc magnets, okay, neodymium magnets, and these are safety pins. And what we have here is a copper wire which is encapsulated and then made it into a loop, right? So what is happening here is very simple. When current passes through this, there is a torque on the loop, okay? And why is there a torque on the loop? That's because the current is passing and there is a magnetic field which is acting on the loop, okay? And that magnetic field gives you a torque, and that torque is causing this loop to rotate, right? So this gives you a very simple example of a DC motor, and if you actually study the textbook, it's not very easy to understand, okay? So if you make this with your own hands, you will find it really easy to understand electromagnetic induction, okay? And you can actually place the magnets in a different place and see how that affects the rotation and so on, okay? You can change the batteries, for example, you can put a more heavy duty battery and see how does the rotation speed change, right? And you will also see that if the contacts here are not made well, the rotation again gets affected, okay? So I would encourage all of you to go ahead and make these things. These magnets, whoever is in Bangalore, you can buy them in Care Market, or if you are, you can also buy them on Amazon. They are very easily available. They are not very expensive as well. Okay, so do try them out. And Mr. Vinayak can show you some simple thing that you can do with straws. So this is how you can understand, for example, waves. Now, why we are doing this? We are doing all of this because these are simple things that you will find around you, and you should be able to make these things ask questions, be curious. This is the National Science Day, right? So we are celebrating science. So you can see here, for example, this is a beautiful example of how you can understand wavelength, the concept of wavelength, for example, and the propagation of a wave. Okay, so if how to do this, you can see how the wave is propagating. Okay, and the propagation of a wave does not involve the propagation of particles, right? It's propagation of energy. So how none of the straws is actually moving from there here, right? It's only the energy that is going from one end of the one end where Mr. Vinayak is holding to the other end and then back as well. Okay, so we will end this session here, and thank you for joining us, and maybe we'll see you here after this corona thing is over, after this corona monster goes away. Thank you, everyone. Thank you. Thank you, Sebastian. Thanks all of you for coming on Sunday and then destroying your Sunday. You could have gone back actually. You were saying you were planning to go.